Hi everyone. Going to start to talk you through the kinetics of acetone iodination. Now this is a classic experiment. I kind of mentioned it in the notes a couple of times. It's where you can actually monitor the disappearance of iodine, which is kind of a brown purpley color solution, by your eye, right? And it's kind of an initial rates method using basically your eye as a detector. So it's kind of a classic. And what we've done actually, we've taken just the experiment from the classroom, the lab, and we've just given you data. Okay, so what I'm going to do is give you my regular in-class Prelab, and that'll give you everything you need to kind of answer, the questions from the lab and to complete the experiment. And we've simply just given you a data set. Okay, so you go to, this is, just make sure we understand it's not a pivot lab. Okay, so you're going to go to GRP 102, download this thing, which is the experiment package, which you'd bring to lab in a regular semester, and then you're going to download a data set based on your birthday. So you just make sure you follow the instructions at the GRP 102. So it's a little bit different than the ones we've done so far, in that it's not, repeat, not a pivot lab. Okay, now my pre-lab basically follows through what's talked about here. Okay, but in kind of in the way I talk about it, right? So let's take a look. Of course, I need a pen. I don't have a pen, so excuse me a second. So I got myself a pen. Okay. All right. So, the experiment is called the rate of. Let me just write it down. The rate of iodination of acetone. Yeah. Okay. So we know that, right? Now the objective basically is for you to develop the rate law equation for this reaction, okay? And it's the quantitative. Determine the quantitative. In other words, you need numbers, right? So you can have orders of reaction, and you can have the units and value of K, right? Determine the quantitative rate law equation for, here's your reaction. This is acetone, this is nail polish remover, C3H3O aqueous. So we take a solution of that, add it to iodine solution in the presence of a catalyst. Now H plus doesn't get involved in the reaction, I'll put cat there, but it does speed it up. Well, it's a catalyst, right? So we'll figure out its order and how important it is later, but it's a pseudo-reactant, right? It may or may not speed up the reaction for 0 first or second order, in other words, right? But it has to be in our equation, okay? Turns into the iodinated product plus I minus. Okay, now this is colored so we can see it, right? So it's a reactant we can monitor literally with our eye. If we know how many moles per litre we start with of I2 and then count how many seconds it takes to go away. Oh, that's the rate, right? Okay. So, where of course, rate equals, it's going to be K, reactants to some powers. And I should say, make sure you read through that Kinetics 2 packet and understand it, try some questions before doing this lab, okay? Oh, and talking about this lab, I've actually set it due for Sunday this week, right, when you watch this. Because remember, the two labs are due this week. So one's going to be due on Friday, which is the HCl one, and the other one, this one, is going to be due on Sunday, so give you a little bit more time there. All right. And both of them, the reason that the first one was delayed is because you need to get through Kinetics 2 to get the theory, right? So hopefully, you'll have the theory in place by then, other reactant, and then the catalyst, pseudo-reactant, mention that in the notes, and we don't put 0 or O, we just put P, right? So we're going to put in values for N, M, and P, and the value in units for K. Okay, the rate comes from measuring the rate of disappearance of iodine just by vision, by sight, right? Okay, so we need to find K, M, N, and P. So it's very similar to those 2 or 3 examples we did in Kinetics Packet 2 with the initial rates method. Now, as I mentioned, this is a a classic experiment because it has a variety of really cool tricks we can use, which actually helps us out, right? Okay, so number one, I2, as we mentioned, is purple / brown, all right? So can monitor by I, all right? So if you know how much iodine you have to start with in moles per liter, at the end when there's no color, because it's a reactant that disappears, right? So, 2 moles per liter disappears over 1 minute, right? It's 2 moles per liter per minute as a rate, isn't it? Right? That's not the numbers we'll use in the experiment, but that's the idea, right? So you can set up an experiment where you know I2 concentration. You literally measure with a stopwatch how long it takes for the color to disappear. Concentration divided by time is initial rate, and we'll show you a trick again in a second. Initial rate for I2 disappearance. Okay, so we're going to measure rate with respect to iodine. That's the bottom line. Okay, we're going to measure rate with respect to iodine. Okay, now 2. It's kind of a giveaway, right? In the regular semester, I actually have students do this for extra credit. You don't need to do it. It's not even in your data sheet, right? But the order with respect to iodine is 0, and that's just an assumed thing, right? Now, if this was the real experiment, I've had my students doing it for extra credit do the iodine trial first, right, where they double the concentration of iodine, and it'll take twice as long as everything else because it's 0 order, it's the slowest, right? So in this one, we don't actually test it, it's just assumed, right? So your data sets, we don't even use it, but hey, we're going to go with then P equals 0 up here, right? So P is, oh, sorry, not P, N equals 0. There you go. All right. So N's going to be 0. So really you're finding the value of M and P, right? Because we're going to assume N is 0. All right. Now, so the rate, remember we're watching iodine, change in iodine concentration, right, from time 0 over the time it takes, right? So, oh, moving up. So the rate of our, or speed of our reaction is measured with respect to iodine, okay, so I2. So how long does it take for the iodine to disappear with time? And that's going to be, if I go back to my equation up here, this number, okay? So the rate, or the speed, we're going to work out with respect to iodine. That value, which we actually figure out by counting how long it takes X number of moles per liter to disappear, is a thing we know, okay? So we'll know that from our experimental data, okay? Nice and easy. We'll show you how to set up the tables in a minute, but that's it, right? Okay. This allows to set up initial rates. Okay, so because we have this, and what we do, trick, set I2 to be very, very limiting. All right, so we set the amount of iodine in the solution as a tiny value, yeah. And if you think about it, if the other two values are bigger, right? Okay, so for acetone and H+, right, they're bigger concentrations, and iodine is small, yeah. Okay, then when we change the concentrations of the other two, right, we'll get their initial rate because, you know, iodine will be gone in a second, right, and we'll get the rate. Okay, so it is the initial rate because we make the iodine concentration super small, so it disappears relatively quickly. So that's an experimental trick, right? That's the experimental trick. Okay, so bottom line is, it's kind of a MacGyvered initial rates method, and the initial rates method absolutely applies, right? Okay, now, when we actually look in our experiment, remember, if you remember the clever trick we used where we have a baseline, where we literally have the concentrations of things at kind of a lower level, then we double one of them, double the other one, right? Okay, and then compare the baseline and do that kind of dividing math, yeah? So you're going to have to look at that dividing math. I'm not going to go through that because that's nicely explained in the packet. But I will show you where we set those numbers up, so when you divide them, you get the 2 factor, yeah? Okay, all right. So when we look here Okay, and the numbers are actually, I think this is actually filled out, and this is filled out. Okay, both of these are filled out in your birthday data set, right? So choose that data set based on your birthday. Okay, now what we got here, we have to, and here's one I prepared earlier, right? Okay, so in class we'd make a big fuss of this. We'd actually go through, we'd put this table on the board, yeah, and we have the baseline, and we'll look at that in a second, right? So that's when we have all the concentrations at the lowest, and there's a lot of dilution in this, yeah, so you've got to be real careful, and should we do this in class, we'd talk about the math more, but I'll just give you the numbers, okay? We're adding 10.0 milliliters of 2 molar acetone, right? 10.0 milliliters of 0.5 HCl, okay? And then, what is that one? Yeah, 30, oh, no, sorry, my mistake, 10 of iodine. And that's 30, right? And we'd bring it up to 50 altogether. Each one of them adds up to 50 milliliters, so we need 30 of water just to top it off, okay? So that's trial one. Okay, and down here we'll work out the concentrations in a second, yeah? So very simply though, if you think about it, right, if I got 10 milliliters of acetone in a total of 50 milliliters, oh, that's 20. I've got 50 milliliters total, 10 milliliters is acetone, so it's actually a fifth of its original concentration. And that's the math we go through in class, right? So down here it's not 2.0, it's a fifth of 2.0, which is 0.4, right? Which we'll do in more detail later. Okay, all right. So, and then what we do, remember, if you remember, what we do, measure the temperature. It's probably 25 degrees C or thereabouts, right? Whatever the lab temperature at the time was, okay? Now here, you do 3 trials. In lab, you'll do trials until you get within 20 seconds, right? So you throw all these things into a beaker, you swirl it, and you put it down, and the reaction started, right? And as soon as you swirl them, you press the start and the stopwatch. And then you just count until the color disappears, right? And you write down a number of seconds here. So maybe it's 7:20 seconds, 7:10, 7:15 or something. And that's good because they're all kind of reasonably close, right? And then to find out the rate, which we'll do down here, it's just the concentration of iodine divided by the average time the reaction took, all right? But anyway, you've got to set it up first, right? So here, what we're going to do, right? So in the next one, remember, it's all going to add up to 50, right? So I'm going to use twice as much of this, same, and 10 less water, yeah. So that's actually 30, 40, 50. Looks like 20, 30, 40, and then 10, 50. Okay. I think that's right. I think it's 50 milliliters. It may be 60, right? So these might be 10 more each time, but either way, we're doubling this one. Okay. And then finally, 10. Remember we change this one. 10. Remember this one is kept constant because, we could do a 4th trial and test iodine, but we've already told you it's 0. Okay. And that's 10. Okay, so there are our raw data sets, yeah? Every time we're comparing to baseline, okay? Every time we're comparing to baseline, and then we systematically double the reactants we're interested in, yeah? So when we do that math, so experiment 2 divided by experiment 1, we're finding the rate with respect to acetone. Experiment 3 divided by experiment 1, finding the rate with respect to HCl. Should we have done a 4th, we'd have doubled that one, and we'd find it with respect to I2, but it's given at 0, right? Okay, now, down here then, when you actually look, and again, this is filled out in your sheet for you, right? When you actually figure out in experiment 1, experiment 2, and experiment 3, what the actual concentrations were, you just take the concentration and, it's a 1 part in 5 essentially, so it's divided by 5, right? And then 0.1, 0.001, 0.8, 0.1, 0.001, 0.4, 0.2, 0.001. Okay, fair enough. So this is where we see the doubling and the doubling, right? And iodine is kept constant in each case, and these are our variables, right? So this is our, essentially this is the rate equal, I'm going to write it backwards, K, I2, H plus, acetone, M, N, P, right? So it's kind of the rate equation written backwards. And over here, how do you get the rate? Well, it's just this concentration divided by the time, right? So this number divided by the time, 710 or whatever, equals the rate in moles per liter per second. Okay. Now, gotta be super careful, right? Gotta be super careful. Once you have this, this looks just like your notes. This looks exactly like your notes now, right? However, very, very important, right? So if I go down here, let me write out rate equals K. Just put AC for acetone. H plus. And then because iodine is zero order, I don't have to write it. It's I to the 0 is 1, right? Okay. So there's my rate equation. Yeah. Okay. So I'm going to compare 2 with 1, divide them out. I'm going to compare 3 with 1 and divide them out, right? That's just like we did in the book. And you have to do the math method because these numbers for rate are not going to be nice numbers. Careful, right? So even though you doubled here, right? So remember the concentration factor to the order equals the rate multiplier, right? Okay, the rate multiplier is not going to be like 4. It might be 3.5 or something. So yeah, unfortunately, and this is where a lot of you are going to lose points, I'm telling you right now, okay? You're going to have the concentration to the order. So if I compare 2 and 1, yeah, we doubled here, right? Okay, so 2 to the M equals some value, right? I'm going to pick a number, right? I'm going to pick a number 3. Yeah, maybe it's 2.5, right? Let me just pick a number 2.1, right? If it was 2 exactly, it'd be first order, wouldn't it? Yeah, it would, right? If it was 2 exactly, 2 to the power 1 is 2. But it's not, so you're going to have to do some log math. So you got to remember that log of n equals x, then n log n log y, okay, equals n log y equals x, okay? You got to do this log math to actually solve for x, okay? So that's kind of difficult, yeah, okay? Well, more difficult, right? So you cannot do this by observation. You have to do a little bit of clever math at the end, okay? So if you start from a position like this, be able to do, actually I should do it properly, shouldn't I? Take the log of both sides. So if I do that over here real quick, m log 2 equals log 2.1, right? And you can take it from there to solve for m, log 2.1 over log 2, right? Yeah, okay. So you can do that, and you can get the order, right? And then you round, because it's either 0, 1, or 2, right? Okay, so it's either 0, 1, or 2, and then write in that integer in here, yeah. So actually you could write both. So maybe it's like, 0.95 or something, and then you put approximately equal to 1. Okay, but I want the actual numerical answer that's a non-integer, and then you round up or down, okay? Okay, hopefully that makes sense. All right, now, when we look at the rest of the assignment, you find your values of m and n, okay? So you have rate equals K, acetone. I'm going to pick a number. It may or may not be the number you get. I'll just say 1, right? Okay, and then it might be, let's say H plus. It might be to the 2 or something. These may or may not necessarily, right, be the ones you get, yeah? Okay, so once you've figured these out, then remember what you do. My suggestion is just use it for the baseline. Or actually, you should probably do it. Actually, I want you to do it for all 3, right? So for all 3 experiments, yeah, rearrange to find K as the subject, like we did in the notes. Okay, put the units in. Don't forget, because the unit's going to be unique, right? Okay, find the value of K with its units 3 times. then take an average, and then it says write a complete rate law expression. So you take this down here, and you put the numbers and units in it, right? So you have numbers, number and units, and that's the quantitative version of the rate law expression. That finishes your experiment, okay? It's not too different than the 2 assignments in the book, but the numbers are experimental numbers, so you have to do actual log math to find the true value of the powers and then round up or down to get an integer. All right, then you move on to questions. So there it is. Okay, so it's the classic 3 reactants for little experiments, right? So it's just like the ones in the book. Determine the complete rate law expression. I'm going to put equation, right, including the value of k with its units. All right. So if you look here, you know, you got to be careful. You got to this is where it's. Remember when I said in the notes, careful how you set it up, right? So if you're smart, you do the baseline and then systematically double reactants, right? That's not necessarily what that happened here. So you're going to do that simultaneous math, start dividing stuff out, and it's going to be a bit more complex. It's going to be a bit more of an in-depth simultaneous math equation, right? But once you get 1 power, yeah, it kind of snowballs from there. So that takes a little bit more thought, right? Okay. Feel free to discuss with others at the discussion/water cooler. Okay. So on the whole, a pretty nice experiment. I really like doing this one in the semester. Okay, it really kind of is a nice kind of hands-on example with a simple experiment that shows the first, you know, the initial rates method in action. Okay, so again, any questions? Water cooler chat, discussion here. And again, this one's due on the Sunday, giving you a little bit more time because we had 2 labs due this week. Okay, stop there. See you guys next time.